Seoyeon Park from the KGSEA Math Circle, and today I'll be presenting about fractals and patterns in nature. First of all, what is a fractal? A fractal is a pattern where small parts look like the whole. This means that it shows self-similarity and that a small part of the shape looks similar to the whole shape. When you zoom in on a fractal, you continue to see the same shape of pattern repeating itself at different scales. Unlike simple geometric figures such as triangles, circles, or squares, fractals are not limited to one scale of size. This can be infinitely complex even though the rule that generates them is usually very simple. This idea of infinite repetition and complexity is the defining property of fractals. A simple example of fractals that we could easily see in nature is a coastline. This is also called the coastline paradox. Self-similarity can be seen clearly in nature. For example, a tree as a whole has a certain branching structure. If you cut off one branch and look at it carefully, you can see that it has the same shape of branching structure as the entire tree. If you go even further down to the twigs, they also repeat the same structure. Another example is a fern leaf. A large fern leaf is made of smaller leaflets, and each leaflet has an even smaller structure that repeats the same pattern. This shows that self-similarity is not only a mathematical concept, but also a natural process for growth. The Koch snowflake is one of the most famous mathematical fractals. Starting from the base or the starting figure, in this case a single line, divide the line into 3 equal parts. Then on the middle, an equilateral triangle is constructed. After that, the base of this triangle is removed, leaving a shape with 4 line segments instead of 1. This is the first stage where the original line becomes more detailed and the snowflake pattern starts to emerge. In the next step, the same process is applied to each of the 4 line segments. Each line segment is divided into 3 equal parts, and a triangle is added in the middle. With every repetition, the number of line segments increases and the figure becomes more detailed. After many repetitions, the figure begins to look like a snowflake. An interesting property of the Koch snowflake is that its perimeter becomes infinite as the process continues forever. However, at the same time, the area inside the snowflake remains finite. The Sierpinski triangle is another well-known fractal. It begins with a single large equilateral triangle. This is the initial figure before the process of repetition begins. In the second step, the middle triangle is removed from the large triangle, leaving behind 3 smaller triangles arranged in the same overall triangular shape. At this stage, the figure already starts to show the property of self-similarity because the 3 smaller triangles resemble the original triangle. In the next step, the same process is applied to each of the 3 remaining triangles. From each one, the middle triangle is removed again. This creates 9 smaller triangles. The process can then be repeated infinitely many times. As the number of steps increases, the figure becomes more and more detailed and the empty spaces grow larger. Eventually, the area of the figure tends to 0, while the border becomes infinitely complex. This demonstrates another way that fractals can combine simplicity with infinity. The Mandelbrot set is the most famous fractal in mathematics. It is defined by a very simple equation involving complex numbers, but the resultant figure is infinitely complex. When you zoom in on the edges, new structures and patterns appear endlessly. In many places, you can even see miniature copies of the entire Mandelbrot set hidden inside. The self-repetition and infinite detail make the Mandelbrot set one of the most studied and admired objects in mathematics. Fractals are not limited to mathematical figures. They can also be found in many natural objects and processes. For example, the whole broccoli is made of repeating spiral patterns, and each smaller piece resembles the larger one. Lightning also branches out in a fractal way, with each smaller branch looking like the entire lightning bolt. The surface of mountains and coastlines shows fractal properties because no matter how closely you look, they still appear rough and irregular. The branching of trees and the structure of leaves are also fractals in nature. These examples show that fractals are a fundamental part of the natural world. Lastly, fractals are also used in art and technology. Artists often use fractal patterns to create designs that are both simple and complex at the same time. In computer graphics, fractal algorithms are used to generate realistic natural scenes. For example, the rough surface of mountains, the shapes of clouds, and the flow of rivers can be simulated using fractals. This allows movies and video games to create realistic environments without needing to design every detail by hand. Fractals are also used in signal processing and antenna design because their repeating structures can be efficient in both space and frequency. In conclusion, fractals are shapes and structures that show self-similarity and infinite complexity. We saw how simple rules can generate fractals like the Koch snowflake and the Sierpinski triangle in abstract mathematics, also in nature, art, and technology through natural objects, realistic graphs, and efficient designs. Fractals show us that simple rules can produce extremely complex and beautiful structures. Thank you.